Hi folks, so just have this little demo to kind of point out some of the features of the motion of the simple harmonic oscillator. So on the left-hand side here, you can see you've got this spring which is oscillating up and down, and this is executing simple harmonic motion. And I've arranged it vertically here so that you can kind of see the position as plotted will kind of match with the kind of position of the mass. So you can see to begin with here, we kind of have it at its lowest extent, so it's at its maximum amplitude kind of extended, and then we come up here, it's now at its maximum compression, if you like. So now the spring is completely compressed, and it kind of executes this oscillatory motion as we discussed in the class. So what's interesting to kind of look at then is the behavior of these other quantities, the velocity and acceleration. We're not going to worry about jerk. If you're interested, jerk is the derivative of acceleration with respect to time. It's important in engineering, but we don't need it for our purposes. So if we think about what's happening to the mass here, at the end point here, and you can see that it's kind of, as it comes down towards the lowest extent, it's slowing down, and it actually then, its velocity changes direction. So it's previously moving downwards, and then it starts to move upwards. Here it's moving upwards, and it starts to move downwards. And of course, what this means is the velocity must be zero at this point. Okay, and we know that as well because the velocity is the derivative of position with respect to time, and we know that the derivative of this top part of the curve here it's flat, right? So the derivative goes to zero, so the velocity must also go to zero. So if I switch on the velocity here, you can see that indeed at this point where the position is maximum, the velocity is indeed zero. And it actually starts at zero as well. Okay, so where I am at the kind of peaks and troughs in position, my velocity is zero. Where is the velocity maximal? Well, when my position is zero. Okay, so when I'm kind of going through here, you can see this is where the gradient of this blue line is the largest, which then implies that the velocity is the largest. So what that means is that the mass is kind of speeding up, speeding up, speeding up. Now it's at its largest extent, and now it starts to slow down again as it reaches as the spring becomes compressed, and that's because of the force of the spring. Okay, so the force of the spring is acting to accelerate the mass. It reaches its maximum velocity then when the spring is at its equilibrium position, and then it begins to slow down as the spring compresses again, and the force begins to push the other way. Okay, so that's how our velocity behaves, kind of in anti-phase with our position as we would predict from the formulas. But then, of course, we can turn the acceleration on as well. Acceleration we know to be the derivative of the velocity with respect to time. And as a consequence, we expect it to be the second derivative of the position with respect to time. And because we have this oscillatory motion, it's going to be minus the position. So where our position starts at the bottom here, our acceleration is maximal and positive. So what that means is the mass at this point, at the start of our motion, is being accelerated upwards. So the acceleration is at its largest value, and that's because the spring is at its largest extension, so it's exerting the largest force, and force is equal to mass times acceleration. So our acceleration is large and positive here. Once again, when the position is at zero, the acceleration is also zero. That's because the spring is now neither compressed nor extended, so there's no force being extended. And then when we reach the very top of the motion here, the acceleration reaches its this trough, which means it's very large, and negative, meaning that we are now going to be accelerating our mass downwards. Okay, so we've reached this maximum position. So we end up with these three curves here, which are all oscillating with these different phases, but they're all related to each other because acceleration is the derivative of velocity and velocity is the derivative of position. But we can understand all of this in terms of the spring force and in terms of the acceleration that spring force exerts. We can also play with the size of the various different constants here. So here we've got a mass of 1 and a spring constant of 1. What that means is our angular frequency is 1. And that is why these quantities all have the same size. So you can see that the position and the acceleration and the velocity all have the same magnitude when I run this. Okay, they all have the same magnitude. And if you look at the formulas that we derived in the lecture today, you'll see that makes sense because the velocity has an amplitude of omega times xm, and omega is just equal to the square root of k divided by m. So here that's going to be square root of 1. So that's why these all have the same amplitude. But if I start to change that, so if I now have a higher spring constant, if I increase k, what this now means is that these quantities have different values. So the velocity has a slightly larger value, larger maximum value than the position, and the acceleration has a slightly larger value than the velocity. And that's because we are multiplying now by some larger number. You can also see that the frequency has changed, okay? So for a larger spring constant, I actually have slightly faster oscillations. I can go up again, and you can see now I have faster oscillations again. So I fit more oscillations in the same amount of time for this larger value of the spring constant. And indeed, if I make the mass lower, I go even faster again. So you can see I get larger oscillations in the acceleration and velocity. It's getting a bit messy there, so I'll just clear it up. But it also goes much faster. So lower mass, higher angular frequency gives us a much higher kind of frequency there. The offset thing here, then, this corresponds to our phase. So if I start at an offset of 1, this corresponds now to a very small, you can see I'm not starting at the equilibrium position, but there's a little offset in the phase. I can change that offset, and it basically changes where I start. So this is just a different way of discussing the phase. But I'll put a link for this little applet so you can have a play with it. You can see how the different terms affect things, and also try to get a feel for how velocity, position, and acceleration are related in simple harmonic motion.